Welcome listeners to the second part of our discussion on volcanic activity. And like we have seen the different types of volcanoes, starting with the active one to the extinct one and intermediate one, and how the volcanoes are erupting on the surface of the earth, be it your basaltic magma or your granitic magma, and how the composition of the lava will have an effect on the overall geometry of the volcanic cone that we have discussed. Apart from that, we have also seen the possibly the best example of how it can impact human lives and livelihood. The next part will be looking at that how or where to find these volcanoes in space and time, as well as how explosive these volcanoes could become based on its various parameters, as well as what are the other features that are associated with volcanoes that we'll be also discussing in a bit. So to start with that, we have known for ages or since even before the conception of the idea of the plate tectonic theory, people have recorded that there are several volcanic mountains or volcanic islands that are present almost circumferencing the Pacific Ocean. So this volcanic chain is also referred to as the Pacific Ring of Fire. So earlier, obviously, there was no suitable explanation for that, that how or why these volcanic chains are present in such a way. But now, obviously, with the idea of the plate tectonics, we now know that how this ring of fire is associated with the Pacific plate. So your Pacific plate, just in this case, with respect to the Pacific ring of fire, your Pacific plate is getting subducted on the western side, northern side, eastern side, southwestern side as well. And obviously there is your East Pacific rise, which is again a mid-oceanic ridge, and the other part or the other half of the Pacific plate on the other side of the East Pacific rise is your Nazca plate, which is again getting subducted beneath the South American plate. So here you can see a continuous zone or chain of volcanic islands that are present along on the margin of the Pacific Ocean as a whole. So obviously these volcanoes are related to your convergent boundaries, because these are the zone of subduction where your new volcanism is taking place, and mostly these are, again, apart from a few, mostly these are whenever these are continental arc, these are andesitic in nature. When they are simply volcanic arc, they are basaltic in nature. So you can see there is a continuous range or chain of volcano that are present along this Pacific ring of fire. Apart from that, also you can see other subduction zones like this of the Java Trench, or the group of islands that make up Indonesia, the Java Sumatra chain or trench. There also you will get sequence or series of volcanoes that are present here. Also, one of the volcano that is believed to be connected with this chain is present in our Andaman and Nicobar Island, your Barren Island as we know it now, which is again giving you a lava mainly of composition, basaltic composition. Sometimes basaltic andesite is also getting outpoured on the Barren Island. So obviously your convergent boundaries are your sites of your volcanism. Apart from that, also divergent boundaries are also your sites of volcanism, like we have seen the volcanism in the mid-oceanic ridges. Obviously they are not violent in comparison to that of the volcanoes which are associated with the convergent plate boundaries or the subduction zones, but there are always volcanoes that are associated with the mid-oceanic ridge. That is why that continuous new ocean floor is being created at the mid-oceanic ridges. So that is why there is continuous volcanism, strictly basaltic in nature, that is making up the new basaltic oceanic crust on the ocean floor, and that makes up the ocean floor. So 75% of the Earth's volcanoes here, I can say, are that are more than 450 volcanoes are located along this Pacific Ring of Fire, and 90% of Earth's earthquake as well, because these are again your earthquakes are very characteristic of your subduction zones. So they are also associated with this ring of Pacific Ring of Fire. So apart from that, you have volcanism in the convergent boundaries, you have volcanism in the mid-oceanic ridges, which are obviously of non-violent type, which is making up the oceanic crust. But the third kind of volcanism is a result of hot spot. We don't exactly know till now. There are conflicting or debatable ideas on the zone on from which your hotspots are derived, or your hot molten material that is coming. It is believed that it is coming from the D double prime layer, which is the boundary between the outer core and the lower mantle, or you can simply say the core and mantle boundary, that is also referred to as the D double prime layer. So it is believed that due to some changes in the pressure conditions, some hot molten material that is resting just above the core in the lower mantle, they start to flow from that level to the upper part of the crust. But remember, this is not like a fluid material that is coming up, it is more of a viscous rock mass that is finally coming up to the bottom of the, you can say, the bottom of the lithosphere. Then it goes into decompression melting. Finally it generates lava, or you can say magma, that is outpoured as lava at the hot spot volcanic sites. So your volcanism, apart from the Pacific Ring of Fire, or even apart from the mid-oceanic ridges, there are several sites of volcanism which are mostly intraplate. Apart from a few of them are also interplate, like we get to see volcanism in the Iceland. So Iceland is that part of the mid-Atlantic ridge which is simply above the mean sea level. So this is, you can say, the presence of the mid-oceanic ridge on the surface is the reflection of the country of Iceland, and that there also Iceland also have a series of volcanoes, but it is believed that those volcanoes which are present on the surface or the land surface of your Iceland, they are strictly related to a hotspot that is sitting beneath that region. So your hotspot, these are the several locations of the hotspot around the earth, which are sometime coincidentally, they are also coinciding with your the zones or locations of your mid-oceanic ridges, but it is not like they are strictly oriented or they are present along with the mid-oceanic ridges. They are distributed, you can say, sporadically throughout the earth. There is a reason, actually this distribution is also not that sporadic, but that is not a point of discussion at this level. It requires some advanced level understanding of geophysics as well to know that why the hotspots are located in such a manner. So if I think about now about the generation of molten material for the hotspot volcanism, so like I was mentioning, it is coming from the deepest part of the mantle near the boundary with the outer core. It is referred to as the D double prime layer. So this rising plume, what we refer to as the mantle plume, will come up to the bottom of the lithosphere. Here it will go under decompression melting, resulting into the volcanism that we can see on the surface of the earth, forming the volcanic cones. So one of the best example of this mechanism of hotspot driven volcanism is the Hawaiian Islands. There is again a specific geometry of the Hawaiian Islands, and this is due to a reason. We will not go into detailed discussion of that, but strictly here we will stick to the mechanism of hotspot volcanism. So in Hawaii also there are several volcanoes which are related to a hotspot that is sitting beneath the your Hawaii hotspot in the Pacific plate, that is sitting beneath the Pacific plate. So here again, if I look at this diagram, so a rising plume is coming up from the contact of the core mantle boundary, and it is coming towards the surface like this. And like we all know that plates do move in space, so a plate, whatever plate is sitting above that hotspot or mantle plume, is moving in some direction, be it northerly, easterly or westerly, in whatever direction the plate is moving. So once the mantle plume reaches the bottom of the lithosphere, it goes into decompression melting, and finally it results into the outpouring of the flood basalt on the ocean floor like this, resulting into the formation of the volcanic cores or the volcanoes on the ocean floor, like that of the Hawaiian chain of islands. Now, if I look at this idea that if this is the mantle plume, it is simply getting stuck or getting attached to the lithosphere. So, as the plate move, if I take the example of Pacific plate itself, I can say that Pacific plate is moving towards westerly to northwesterly. In that case, if the Pacific plate is moving above the hotspot, if this is the hotspot we are thinking about, or the mantle plume that has now reached the bottom of the Pacific plate or the lithosphere here. So now the Pacific plate is continuously moving. So what will happen? Some molten mass or the molten material will try to get attached to the bottom of the Pacific plate, and it will move along with it to a certain distance, not to a very large distance, but it will move up to a certain distance. So from that you can say there will be volcanism obviously at the point where it is simply protruding the lithosphere. So there will be volcanism there, but as soon as the plate moves, this volcano which was earlier active will now go into extinction. Why? Because there is no more supply here to support the continuous volcanism that is taking place on this surface of the Pacific plate. But if it goes on and on, then what will happen? That more and more extinct volcanoes will be present along its chain of islands, which are also referred to as your hotspot trail. So hotspot trail are nothing but these are the chains or the trails of volcanoes which were active at certain point of time when it was sitting just above an active plume. Now the plate has moved above the active plume. It is not like the plume is moving, it is actually the plume is fixed, because it is coming directly from the deeper mantle. It is coming directly in a straight manner, in a straight manner, and the plate is moving on just above the place of the main hotspot volcanism. So as the plate moves on and on, what will happen? It will bear signature of its older extinct volcanic islands on the surface, and there will be new volcanism that will take place at the source of the hotspot. So new volcanism will take place here. In this diagram you can see new volcanism is taking place here. The rest are obviously extinct volcanoes, and some of them have even modified into your sea mount, like we have discussed earlier. Earlier it was a volcanic island, now it has been modified to a sea mount due to process of erosion over the time. So based on this also, people have calculated the movement of different plates, the absolute plate motion of different plates based on the fixed location of a mantle plume. So if you have a fixed location of a mantle plume and you know the age of each and every volcanic island, then you can also predict the time required to move from that source of the mantle plume to the present position of the volcanic island or sea mount. So based on the age and the distance from the present position of the mantle plume, you can also calculate the velocity vector between these two. So you can have an idea about the plate motion if you simply use the reference of hotspots. Then talking about that whether volcanic eruptions are violent or not, there are different classes of volcanism based on its explosiveness. So the quest or the very means you can say the lowest explosive kind of volcano you will find in Iceland and in Hawaii. So Iceland again, it is that part of the mid-Atlantic ridge which is simply above the mean sea level. So it is actually a mid-oceanic ridge, and beneath it also there is a hot spot, that is Iceland hotspot, referred to as the Iceland hotspot. So there the volcanism is again mostly basaltic in nature. So the chances of explosive volcanism when the composition of the lava is basaltic is extremely rare, followed by strombolian type which have a higher degree of explosiveness, Vulcanian type, Pelian type and Plinian type. So all these are, you can say, much explosive in nature, and the explosivity of a volcano is extremely dependent on both the composition of the magma or lava it is outpouring, plus the presence of the kind of volatiles in it. So if it is having high amount of water vapor, high amount of sulfur dioxide in it, obviously high amount of sulfur in it, then your explosiveness of that volcano will increase. So based on the simple diagram, the height of the eruption column and explosiveness, you can have an idea that your Hawaiian one is only giving you some ash cloud of means you can say the eruption column is even below 2 kilometers. For strombolian type, it is I will not say extremely violent, but it can be deadly as well. It is less than 10 kilometers. For your subplinian type, it is below 30 kilometers. Vulcanian type, it is near about your 20 kilometer. And for your Fretoplinian type, it is extremely violent and explosive one, which might go the height of the eruption column may go up to 40 kilometers even. So again, this is the, you can say, the explosive eruptive column of the volcano. So this is the largest or the explosive one, that is the Plinian eruption, and the quietest or the non-explosive one is your both Icelandic and the Hawaiian type. This is your strombolian again, this is the Vulcanian, Pelian, and this is the Plinian eruption, which is the most explosive one. So your Icelandic eruptions do not follow the conventional pattern of ash and lava erupting from a mountain summit. Instead, vast quantities of extremely fluid lava pour on the surface through cracks. So that's why there is no question of a specific crater, or there is no question of any explosiveness. Hawaiian eruption are known because they happen pretty frequently, they are very active, and this type of volcano has less explosive activity and erupts quietly due to the very less viscosity of the lava and non-violent nature of the gases present in it. Then you have the strombolian eruptions, the most beautiful volcanic styles, often known as the lighthouse of the Mediterranean, because there are a series of volcanoes along the Mediterranean Sea were called after the volcano that created the island of Stromboli in the Mediterranean Sea. It has a comparatively mild explosion, and as the bubble explode, we discussed about the bubble, that how it will finally means help the lava to become buoyant and extrude on the surface of the earth. It ejects pumice, scoria and bomb. We will be also talking about the solid materials, or what are known as pyroclastic materials related to these eruptions. Then you have the Vulcanian type. The volcanic eruptions are more powerful and are called after eruptions of the volcano island in the Aeolian Islands in the Mediterranean. Again, a famous example is the Mount St. Helens. So these are relatively, you can say, more violent. Pelian and Plinian, these are extremely violent and kind of volcanic activities. The name has been derived from the cataclysmic eruption of Mount Pelee on the Martinique Island in the Caribbean Sea in 1902, and they are extremely explosive, eject highly viscous lava, and are characterized by hot blazing clouds like this. Plinian eruption, these are the most violent kind, massive vertical explosions that shoot gas as and eject miles, even up to 40 kilometers above the volcanic vent. Such eruptions are triggered by highly viscous gas rich magmas. The most severe kind of Plinian eruption is ultra Plinian, where in 186 AD a similar eruption took place in the New Zealand. So now coming, so these are the different types based on the explosiveness of your volcano. Types of your pyroclastic material, again now we will talk about the solid materials that are being ejected from a volcano. So your volcanic ash, that is the finest material. Then you have lapilli or cinders, which are relatively medium sized particles. Then you have the volcanic bombs, large pyroclastic fragments with a diameter greater than 64 millimeter, and the large volcanic blocks, the largest pyroclastic material, which are typically larger than that of the volcanic bomb. So here you can see a scale of the particle size, where your volcanic ash is typically less than 2 millimeter in diameter. Then between 2 millimeter and 64 millimeter you have the lapilli or cinders. Then you have your volcanic bombs and volcanic blocks as well. And sometimes the resultant, due to these are why they are referred to as pyroclastic, because just again by the, if I look at the terminology here, it is pyro means born out of fire, clastic means, like we have discussed in sedimentary rocks, clastic sedimentary rocks which are getting transported from one place to another place. Here in terms of volcano, they are transported, these pyroclastic materials, they are getting transported from the vent of a volcano to somewhere else, or to the farther away from the vent of the volcano. So there is a transportation factor involved in the generation of the pyroclastic material. So clastic means obviously they are getting transported, and pyro means born out of fire. So that's why it is very you can say very appropriate term to define your solid materials derived from that of a volcano, which are referred to as pyroclastic material. This you can say the deposition, and again followed by simple sedimentary processes of your lithification or some compaction. These pyroclastic minerals can also form rocks like tuff and ignimbrite. There are some volcanic rocks strictly formed due to deposition of pyroclastic materials. Here also you can have coarser materials and finer materials. So your coarser materials might get cemented with the finer materials. Simply the finer materials itself can get cemented to form, or consolidated to get form the different volcanic rocks specifically, and some of them are like I mentioned, tuff and ignimbrite are a variety of this one. Type of lava flows, there are broadly again three types of lava flows. The first one is a blocky lava, second one is a mouthful pahoehoe lava, and the third one is a pillow lava. So blocky lava are nothing but again chunks, sharp appearance they will give, composition. Generally blocky lava have very high viscosity, silica rich magma, that's why they form blocks. They can't flow very easily, that's why they form blocks. So form slow moving viscous magma. It is also in the Hawaiian terminology, it is also referred to as lava. The Pahoe lava, which was earlier referred to as ropey lava, is now the Hawaiian term, or the in Hawaiian language it is referred to as the Pahoe lava. So they are smooth undulating surface resembling twisted ropes, that's why they were used to be referred to as ropey lava. It should have low viscosity, a basaltic magma to form such a ropey lava, and obviously the fluidity of the basaltic lava creates this smooth and undulatory surface like that of a bunch of ropes. Then the third type, that is your pillow lava, that will give you rounded pillow like structure, and specifically pillow lavas are formed when your eruption is going on under the sea. or submerged condition. In that case, whenever your basaltic lava goes into solidification, and these are very characteristic of mid-oceanic ridges as well. So if you look at the photographs from your mid-oceanic ridges or the basaltic lava that is making up the new ocean floor, you will see mostly or dominantly they are full of your pillow lava. This is nothing but a kind of geometry that gets attained by a basaltic lava when the volcanism or eruption is taking place underwater or in submerged condition. Then there is a specific character that I would like to discuss a bit, is the caldera that forms in case of when generally a volcano goes into extinction. So after the eruption of a volcano, and if it is getting collapsed, so there is a probability that after extinction the crater gets collapsed. Also it is possible in case of dormant volcanoes as well, but generally it happens with extinct volcanoes. So a caldera forms in different steps. The first, the volcanic eruption happened and magma present in the magma chamber underneath the volcano is expelled, often forcefully. When the magma chamber, now look at the sequence of these diagrams where you have eruptions of ash and pumice on the surface of the earth like this, you have this magma chamber that is sitting beneath the earth. So when the magma chamber empties, the support that the magma had been provided earlier inside the chamber, that gets disappeared. So there is a depletion of the magma chamber, so you are not getting the continuous support of the fluid, or the supply is somehow terminated. When a large amount of magma is expelled, the now empty chamber will be unable to support the entire weight of the mountain structure above it. Thus, a roughly circular fracture, the ring fault, develops around the edge of the chamber. This ring fault serves as a feeder for fault intrusion, which are known as ring dikes. As a result, the sides and top of the volcano collapses inward, and which they gets filled with water. So that's why caldera, you can say, is the fate of an extinct volcano, that if the magma chamber has been depleted completely, there is no more magma is there or no more supply is there to support the huge structure of the volcanic cone, then it starts to, under the action of gravity, it starts to simply form this caldera lakes, or they are also referred to as crater lakes, but this is the fate of a caldera. So there are different types of caldera like crater lake caldera, sealed volcano caldera, resurgent caldera, and explosive calderas. There are some hydrothermal related events also in response to an event of volcanism. There could be a presence of fumaroles, there could be presence of geysers which are associated with some volcano, and also the presence of hot springs. So your hot springs generally develop when there is some hydrothermal vent is present alongside your volcano, or the molten material or the magma chamber is giving you some heat that is getting out from the magma chamber, and the resulting or your surrounding water supply, the water gets heated over the time. So natural springs where groundwater is heated by geothermal energy that is coming out obviously from the magma chamber. So the water seeps into the earth crust and is heated by magma or hot rocks, typically warmer than the surrounding air or ground, like we get to see in the geothermal springs in the Yellowstone National Park in USA, and there are several you can say these hot springs, they are present in the different parts of India as well. There have been certain reports recently from the Ladakh Himalaya region, where there have been reports of hot spring in 2-3 districts in the Ladakh region. Now you also can have fumaroles, openings in the earth crust that emit steam and gases, and often accompanied by some volcanic activity as well. It results from the escape of gases, primarily obviously water vapor from magma chamber or heated groundwater that is present somewhere beneath. Characteristics include high temperature, exceeding 100 degrees centigrade, and also they are associated mostly with your sulfur deposits, or sulfur also gets outpoured along with this fumaroles. Example include the value of 10,000 smokes in Alaska, Italy, and other places in New Zealand as well. Finally, the last one, geysers, hot springs that intermittently eject columns of water like this and steam into the air. Similar to hot spring, but with the added build-up of pressure, they leads to a periodic eruption, and sometimes this geyser can also go means or eject the water and gases along with for a couple of meters as well, means several meters as well. So the characteristic of a geyser include that it occur periodically and catch and reach impressive heights, and examples include the Old Faithful geyser in Yellowstone National Park and other geysers like El Tatio in Chile as well. So here are the different hydrothermal events which are related, not directly, you can say that directly a result of a volcano or subsequent to a volcanism, but these are the events which will give you an idea that some molten material is present underneath somewhere, or some magma chamber is there which might also initiate a new volcanism after a certain span of time. So here I would like to conclude our discussion on volcanism. Thank you.